In today's lecture 18th, we continue our discussion on solving parabolic partial differential equation by classical methods. These are essentially explicit methods, and one of the property of this explicit method is that it brings in its own numerical characteristics as opposed to the physical characteristics. And as demonstration, we are going to show the FTCS method, and we will see that it brings in significant restriction on the time steps. And one of the way to avoid this problem of time step restriction is to switch over to implicit methods, and this is demonstrated today by again considering the heat equation. One of the disadvantage of this implicit method is that we will have to be now solving matrix equation, but fortunately enough for the heat equation, this turns out to be a tridiagonal matrix and which yields an exact solution by using Thomas algorithm. Having adopted the implicit method, one would like to once again go through that stability analysis by the spectral analysis tool, and will establish its stability and its enhanced ability to take larger time step. However, at the same time, when we have periodic boundary conditions or the periodic problems, we need to convert this tridiagonal matrix into its variation called the periodic tridiagonal matrix, and this will be studied in detail. We are solving parabolic partial differential equation, and today we just demonstrated first taking a one dimensional heat equation as given here. Partial derivative of u with respect to time is equal to the second derivative of u with respect to x, and this is defined in a xt plane with spacing indicated by index I along the x direction and j along the time direction. And we specifically talk about a simplest possible explicit algorithm which is called as forward in time centered in space, or FTCS algorithm, and that involves taking this time derivative u of t and writing it in this form on the left hand side. The same way we can take the second derivative of u with respect to x on the right hand side and represent it by this difference expression. Having done that, we note that the points involved in this algorithm are given here by this dotted points, that is u I j plus 1, which is at the advanced time level, j plus 1 is time level, depends on the other 3 points which are given on the line below. In the language of computation, this participating node points constitute what is called as the computational molecule. So, this is what we are going to call as the computational molecule. Now, in looking at this problem, we know that this is a parabolic partial differential equation. So, its physical characteristics are nothing but t equal to constant, and this is what we have as the physical characteristics. Whereas, we note that the node at the advanced time level actually depends on these 3 points, and these 3 points again in turn depend on their corresponding 3 dependent points, that is this one and this one, and for this point and this point. So, what actually means that this point eventually depends on a cone which is defined by a line like this. The extremities of the cone is given by this, and these are what are called as the numerical characteristics. Thus, we understand one interesting attribute of all computing is the distinction between the physical and the numerical characteristics. This is something very fundamental that we will be visiting again and again, and we will point out that one of the goal for the accuracy of the solution depends on how we bring this numerical characteristics as close to the physical characteristics as possible. So, this is a single one, but here we end up getting two branches, right. That is what we get. Now, you can very clearly see that to make the thing work for you, you should have these two sets of characteristics approach each other. How do you do that? A very simple observation is, if I reduce delta t, then what will happen? This wedge will open up towards the theoretical limit, right, the physical characteristics. So, that is what we can do. So, the way to do that, so maybe if I have to make this observation, delta t should be as small as possible. So, that is the rule of the game. that is one of the way, but you already know from your experience in computing what you have done just now. I am going to submit today, that taking smaller time step also makes the process very slow. So, that is not a very good option. That brings us to the question of trying to find out if there are other methods which will do that as desirably as possible, at the same time would not consume too much of time and resources, right. In this context, we start talking about implicit methods, and you can see the motivation actually comes from this diagram that we have here. We want this physical characteristics and the numerical characteristics approach each other. And how do you do it? That is noted here, that what we had done here when I wrote this FTCS algorithm, what I did, I evaluated this at say some node which I called as xi, and I tried to get the time level which I called as Tj, and what did I do is I wrote this as Uxx evaluated. Now, Uxx is evaluated at what level? At the jth level also, right. So, that is also written for the ith node and this, and as a consequence we add this wedge. Now, what we could do is if I do the following, like what we have written down here in equation 15, that we will take the right hand side evaluated at two time levels. Okay. One is at the jth level and suitably blended with the second derivative evaluated at the prior level. So, basically then what we are doing rewriting the right hand side as a weighted average. Okay. How is the weighting done? Of course, lambda has to be between 0 and 1, and then if I do this, what I am doing actually, the first term, if I look at it, would involve these 3 points, right, because I am evaluating that at the j plus 1th level. So, that is what we are going to do. Whereas, this 1 minus lambda times UXX are those 3 points that we had before. So, what we are doing, we are now instead of having a computational molecule involving 4 points, we are having it in terms of 6 points, 6 points. And what we are doing then, instead of taking the value which defines the molecule at these 3 points, we are taking some kind of a weighted average between this point and that point and this point and that and this. So, this is the sequence. So, what happens is, depending on the choice of lambda, we could do many things. For example, if I would set lambda equal to 0, that is, I do not evaluate the derivative at the advanced time level, get everything from the previous one, then we go back to our FTCS algorithm that we can very clearly see. So, this will be just simply that what we have written over there. Now, this is what 2 gentlemen from Cambridge, Crank and Nicholson, they did it in mid-40s. What they said, that take a kind of a unbiased average, take half and half contribution coming from each time level. That's your lambda equal to half means. All right. So, I will take the second derivative evaluated at the advanced time level 50% and the rest of it is coming from the previous time level. Right. Now, we could also, of course, it is a whole continuum. You could choose a value of lambda anywhere between 0 and 1, but we are looking at some very specific cases, and one of which, if I look at, is if I take lambda equal to 1, then of course, this term switches off and all the contribution of the derivative would come from the advanced time level. So, basically then you are going to actually have a computational molecule having these 3 points only, okay? And then what you see, the numerical characteristics is completely aligned with physical characteristics, right. So, that should be the quite a desirable case, and I think this was done by attributed to Lassonen, if my source is correct. And this was, I think, done sometime in that era. Crank and Nicholson suggested this sometime around 46 or 47, and this whole approach of blending the two was suggested by Crandall of MIT, and that was a big game changer in the computing business, that we understand that there are better methods that we could do that will mimic physics better, and in the process you could get your computational methodology also quite efficient and fast. Now, what does it do? What does it do is it actually, now what we had done here, as I had written in the slide before. So, we are doing it UXX evaluated at right. So, this is what we are writing. So, if we are writing that, then of course, we can expand it, and if I do, what I am going to get here is u I j plus 1 minus u I j by delta t. So, this is again Euler time integration, right. This is still the Euler time integration that we are resorting to. All the balancing or subtlety is coming from how we treat the spatial derivatives at different time level. If I of course, write this, I would get, if I call that as delta x square, and then I will get u I plus 1 j minus 2 I u j plus u I minus 1 j, that is this part, and from here I will get lambda by delta x square, and I will write down the same stencil, but now it is evaluated at j plus 1th level, right. So, this is what we are going to get. Now, quite like what we did for the convection equation, we can see some parameters naturally coming out that we already have defined, and we defined the Peclet number, if you recall in the last class, that was simply the ratio of the time step by this. Now, in addition, we also have brought in a extra degree of freedom in terms of this parameter lambda. So, we could define a new quantity which I have called, that is theta will be nothing but Peclet number times lambda. So, that is simply nothing but lambda delta t over delta x square, right. So, you can immediately comprehend that I could simplify this, and I could write down all the quantities which are at the advanced time levels on the left hand side, that would involve this term and all these 3 terms, right. Those are written down here on the left hand side, okay. That those have been written there on the left hand side, and put everything at the previous time level on the right hand side. This basically gives you this equation. So, unlike the explicit method, you realize that now you cannot explicitly pick up the value of the unknown one at a time. What is happening now? Your unknowns are all at the j plus 1th level, right, but they are appearing in a coupled manner, that is the I minus 1, I and I plus 1, they are taken together. So, if I look at that, what does it do? Well, you can very clearly see that you cannot solve it in isolation, right. So, what we are going to do is we will keep, suppose I have a Dirichlet condition, boundary condition. So, that is u is prescribed on this 2 ends, right, at x equal to 0 and x equal to 1, they are prescribed. Then I write down that equation for all the points, right. So, if I keep doing it, then what do I get? I am going to get a stack of equations, right. The first one will involve, if I look at it here, the first one will involve this point and this point. So, 1, 2 and 3. What happens to 1? It is a Dirichlet condition, it goes to the right hand side. So, you are going to have a linear algebraic equation that has the diagonal term u 2 2 and say u 2 3, or it is like this. So, basically what I am saying that I will write this equation, let us say for any j. So, there is no problem, but I will write it for say I equal to 2 first. If I write it for I equal to 2, then I am going to get minus theta and u 1 j plus 1 plus 1 plus 2 theta u 2 j plus 1 minus theta u 3 j plus 1, and everything that has gone on the right hand side, I will just simply write it as RHS 2. Okay. So, that is the whole contribution coming at the point 2 by the right hand side. Now, of course, you can see if it is a Dirichlet boundary condition, this can also be transported to the right hand side. So, that is what I said, that this equation would simply have 1 plus 2 theta, and I will have E 2 j plus 1 minus theta u 3 j plus 1, and I will write this RHS 2 and put a prime to indicate the boundary condition has augmented that what we had earlier on. Now, I could write the same thing for I equal to 3, and now you will notice that this term of course would be there. So, you do not have to you do not need to take it to the right hand side, it is an unknown. So, if that is so, and this I am going to write RHS 3. So, I could write all that. So, what I am going to do is I am going to stack that equation. I will start writing for I equal to 2, then I equal to 3 and write it for all the unknown points all the way up to here, right. So, that is the way the equations are stacked together, and when you put them together you will get a linear algebraic equation like this, where A would have the elements which are given here, right. So, how many non-zero elements that you get? Only 3, right. So, you will get the point corresponds to whatever the I value that you have chosen, okay. That is here, right. That is I will get it as along the diagonal, and this term will go onto the super diagonal, that is the next point, right, in hierarchy. So, basically what we are doing, we are following this sequence, that I will go from left to right and j will go from bottom to top, right. So, if I do that, that is what we are doing. We are fixing a value of j and then writing all the quantities from left to right, and that is why we are getting this equation. A are those coefficients of that left hand side, x is the unknown vector. So, the vector it will be like this, say 2j plus 1, 3j plus 1, 4j plus 1. So, that is a stack. So, I am just simply economizing on space and calling it as x, and this RHS that we have identified here, they all go to the right hand side, right. So, it is a very simple sort of a migration that you can say that we have gone from an explicit method into a business of tackling a linear algebraic equation of this kind, which is A x equal to b. But A has a very neat structure. I think I have it here, that will tell you what it is. It has a structure like this. So, you have the diagonal elements, and you have a super diagonal element, and you have a sub diagonal elements, right. So, you can very clearly identify. So, these are your like AIs, right. These are your AIs. So, if I have to write, so this will be my AI, and this is BI, and this is my CI. So, for every point I am going to get this. Well, you might think why I am giving a subscript here. It is not needed. It is basically constant for all ith point. It is same. But let us discuss for a general case where you may have these things which could be node dependent. Yeah, let us discuss such a case. And let me tell you that this equation, despite its simple appearance, is a central methodology that is used in computing very often. You would come across this procedure of solving this tridiagonal matrix equation, right. So, this is why we are calling it tridiagonal, right. We have the diagonal, super and subdiagonal. So, it constitutes 3 non-zero stacks, diagonal arrays. So, that is why these are called tridiagonal matrix. So, that is your structure of the A matrix, and x vector I noted to you how it is going to be accounted for. So, we will fix a j, run through all the i's from left to right, then migrate to the next j, and so on and so forth. So, this is the sequence that we will be following in cataloging this unknown x. So, whenever you have matrices with lots of zeros, they are called sparse matrices, right. And this particular A matrix is not only sparse, it is also a tridiagonal matrix. So, what happens is, good news in this story is that this equation can be solved exactly, and this is what Thomas did, and it is well known as Thomas algorithm, and this is what we are going to now discuss, how we solve this tridiagonal matrix equation. Well, the logic is simple. I have a matrix A. I could split it into two matrices. Okay. One corresponds to a lower triangular matrix, another would be upper triangular matrix. So, this is a very standard technique that you actually employ in linear algebra, that if you are given a matrix equation with arbitrary A, what you try to do is try to split it up into three parts, like it is called LU decomposition. So, what you have is basically a lower triangular matrix and this is a upper triangular matrix and this is a diagonal matrix. So, in this case what has happened, we have dispensed with the D part, we are just simply writing it as a product of the lower triangular and an upper triangular matrix. And let me just tell you how this is formally done. Okay. Because of that sparseness, so many zeros all over, what we could do is we could write down this lower triangular matrix is like this. So, above the diagonal it is all 0, that is why it is called lower triangular, right. But because of the sparseness, what we notice also that even in the lower triangular matrix also you have a large number of zeros, barring only the diagonal and the subdiagonal entries, right. So, if I decide to call those entries as D 1 in the first row, then L 2 D 2 in the second and L 3 D 3 the third and so on and so forth. So, I have this formal structure. So, it would be our interest to find this out. I will tell you how we are going to find it out, but let me first tell you what we can do with the upper triangular matrix. Upper triangular matrix will also have a similar structure by analogy, right. The lower triangular part will be 0 completely, and the diagonal part here I could have some value, but what I have done here, I have basically divided that by the diagonal part. So, that the diagonal entry has become unity and the super diagonal entries are written as u 1 u 2 up to u n minus 1, right. Now, how do I find these entries L, D and U lowercase quantities? Well, simple thing for you to do is take this L and U matrices, take the product and equate it with what you have with the A matrix entries. Next, we are going to talk about a special algorithm called the Thomas algorithm, which is used to solve in a direct fashion a tridiagonal matrix, which we have written here as the A matrix, which has three entries, banded entries, B i's along the main diagonal, C i's along the super diagonal and A i's along the sub diagonal. And one of the way in which this equation can be very easily solved, this matrix equation can be easily solved is by decomposing this tridiagonal matrix into a product of a lower triangular matrix times an upper triangular matrix given by this. Please note the structure of this lower triangular matrix, which has B i's along the diagonal and L i's along the sub diagonal elements. Rest of the elements of this matrix is identically 0. Also note that the upper triangular matrix has 1 along the diagonal and u i's along the super diagonal. This is one possible way of decomposing the A matrix into L times u, but we could also do a complementary splitting where we could have 1 along the diagonal of the L matrix, whereas the diagonal entries of the U matrix would be not equal to 1. Both are essentially equivalently the same thing, but it is easy for us to realize that we can work out directly the entries of this L and U matrix by performing a product. And for example, if I look at this entry A11, that is this B1 is nothing but product of this first line of L matrix multiplied by the first column of the U matrix, and that is going to give us simply as B1 B1 is equal to nothing but D1. Okay. Similarly, the second entry of the A matrix C1 would be nothing but product of the first row with the second column. That means C1 would be equal to nothing but D1 U1 and so we can very clearly see that U1 is nothing but equal to C1 by B1 itself. Okay. So, basically D1 is defined like this and U1 is defined like this. Now, we can go through this exercise on the second row of A matrix. For example, A2 would be the product of the second row of L matrix multiplied by the first column of the U matrix. So, that means A2 would be simply equal to L2. Now, if I look at the entry B2 of the A matrix, that will be a multiplication of the second row of L matrix multiplied by the second column of the U matrix. So, that means I will get B2 should be equal to L2 U1 plus D2. And finally, on the second row of A matrix, we have the entry C2, and that would be multiplied obtained by multiplying the second row of L matrix with the third column of the U matrix, and that would be nothing but equal to D2 U2. So, what we can see that if we use this as the starting value here, D1 is equal to B1 and U1 is equal to C1 by B1, and then we can easily obtain L2 from this. Since U1 is already available, L2 is available. So, this equation will give us D2, and once D2 is known, C2 is the given entry, we can use the third relation to obtain U2. So, we can see that this procedure can be generalized. We can actually see the generalization emerging from this relation itself. For example, we could write Aj is equal to Lj, and then we could write Bj is equal to Lj times Uj minus 1 plus Dj, and Cj is equal to Dj times Uj. So, as before, we would be able to use this equation to obtain Lj, and this equation we will be able to use to obtain Dj, and the third equation would give us Uj. So, that completes the splitting of the A matrix into L and U. Find the entries of L and U matrices, and that is your original equation A x equal to B. So, suppose I define U times x as G vector, right, U matrix multiplied by the unknown. If I call that as G vector, then this equation is nothing but L times G equal to B. So, in equation 21, what you are seeing, you know the entries of L matrix, you know the B vectors, you can solve for. Why you can solve for? Because it is a simple structure. So, what you can do is you can start from the top. You can take the first row and evaluate G 1, then you come to the second row, from there you can calculate G 2, because this equation will only involve G 1, right. So, we could go through this, that is what I am saying, that G 1 would be equal to nothing but B 1 by D 1, and then once you have that, you can go to any other lines from 2 to n. So, basically in solving 21, you go from top to bottom, right. So, you have exhausted knowing this vector G. So, once you have the G vector, then you will have to solve 20. That is easy, because that also has this sparse bidiagonal structure. So, what you can do is now you can see the last row has only one non-zero entry, and so you can now go from bottom up sequence, right. So, that is what we have done, that if I look at the last one, then this multiplied by G n should be equal to x n, right. So, since I know G n, so that means I have found out x n, okay, right. So, if I figured that out, then if I go to the previous line, that would involve here G n minus 1 plus U n minus 1 into G n should be equal to x n minus 1. So, that is what is a general form of that equation. So, we could write that down. So, since I have a starting value, I can go backwards from bottom up and get the unknowns x. Okay. Now, so this is the way that we solve. Why would we take the trouble of going from an explicit method to implicit method, provided we do not get dividend? So, let us try to find out what do we gain, and the best thing for us to really find out what we are getting in terms of its stability property, because we recall that the fact that we have to apart from accuracy, we will also have to ensure numerical stability. For example, in your assignment you must have seen that if you take lesser number of points, it just blows up. So, that is a sort of a defining sequence of numerical instability. So, here also we do the same thing. What we did here do here is just write down the difference equation, okay. And we will follow the same language by defining this unknown in terms of its spatial dependence, in terms of Fourier Laplace transform, and we are looking at the mth node. So, that is why we are writing x of m, and this is evaluated at nth time step. So, we will do this and we will substitute it here, right. If I do that, well, actually this is a little clumsy work. I should have used some other subscripts, because this I and this iota should not be confused. This e to the power I k x is the square root of minus 1. I think I will go back and correct it and load the correct one. I will exchange these subscripts in these equations. So, if I do that, what I am going to get, as we have done in the that spectral analysis of the 1D convection equation, I will get the same thing. So, now what you are seeing here, that I have a quantity that would be evaluated at T n plus 1, and the right hand side would be all evaluated at T n. So, if I divide both the sides by u k of T n, then this one will give me a G, and because it is also shifted to the left by one grid point. So, that is why I will have this e to the power minus I k h, right. And the diagonal term of course is we are looking at I j point. So, diagonal term will not have any such shift, whereas the last one is shifted to the right, that will give me a e to the power I k h here, right. And of course, you understand theta is retained as it is, and this u j plus 1 and divided by u j, that will give me the g. Okay. The right hand side is a clean expression. So, of course, what you can see here then, well, if you look at it, I could club the first and third term on the left hand side together. So, I have e to the power minus I k h plus e to the power plus I k h, and then I have the quantity 1 plus 2 theta into g, the 2 theta into g, that is on the left hand side, and on the right hand side we could take p minus theta, and that will give us e to the power I k h plus e to the power minus I k h, and the other quantity is 1 minus 2 p e plus 2 theta, right. So, this is nothing but 2 cos k h, right. You will agree with me. Same thing here, this is 2 cos k h, and what we could do then, we could write there minus 2 theta cos k h, and there is a g here, there is a g here. So, I will have 1 plus 2 theta into g is on the left hand side. I will have p e minus theta, and there is a 2 here cos k h plus 1 minus 2 p e plus 2 theta. Okay. So, this I could write it as 1 minus, well, we could write it 1 plus 2 theta, then I will have 1 minus cos k h into g, and on this side I could also get 1 here, and then I could write 2 times theta minus p e. This will give me 1, and from here I will get cos k h. Okay. So, of course, this is 2 sine square k h by 2. So, that is what you are seeing there. So, I am going to get this is multiplied by 1 plus 4 theta sine square k h by 2. Okay. So, that is what you are seeing here down below, because p into lambda is theta, right. So, that is what you see the denominator, and the numerator also similarly is written in terms of this. So, what you can notice is that this is also bounded on the upper side by 1, because I can manipulate it and write it as 1 minus something. So, it is never going to be above plus 1, that is guaranteed for you. So, to guard against instability, all you have to worry about that it should not fall below minus 1, right. So, that is what we will have to do it. And what you notice that apart from the Peclet number, now you also have lambda as a control for you, or you can take the product of the two as theta as the parameter. And now, what we can do is we can obtain the value of g and for various combinations of the parameters. Ideally, I could have done it in a 3-dimensional space. On one side I will have lambda, another side I will have k h, and on the third direction I will have the p. but to make the things a little more understandable, I will show you by slices, right. So, take a very moderate value or low values of P, that is about 0.01, and then plot the G contours in kh lambda plane. Okay. So, this is how you get. The interesting bit is what is written on the top right corner here. This is the range of values of G in the whole space. If you now go back, look at this range, it is ranging between 0.96 and 1, right. And if we look back to our FTCS algorithm, I did not write it, but you can see that it had gone from 1 to some value here, almost 0, there is a 0 line, and on this side we have an instability line, right, which had gone all the way up to the last contour that we show here is -70. So, you can see the dramatic transformation, because this method was unstable in this part of the domain. So, even I am talking about Peclet number of 0.01, I would be looking at here. So, it is quite okay. It is quite okay that it will remain stable, no problem there. However, look at the value of G. This will take all the way from 1 to virtually let us say 0.2, 0.15, that kind of value. Whereas, now by doing this implicit method, I could actually bracket that G between 0.96 and 1, a tremendous improvement, right. So, this is what we get by migrating from explicit method to implicit methods in terms of numerical stability property. Now, if I increase the Peclet number by a factor of 10, so that is what we have done. From 0.01 we have now gone to 0.1, and what do we find? The range is still not too bad, it is still quite okay, it is between 0.6 and 1, it is between 0.6 and 1, and you can realize that this is the story for virtually, this is your explicit method will correspond to what? Lambda equal to 0, right. So, you can see this is your explicit method and this is your implicit method, fully implicit method, and you can see that there is a significant improvement here, that we do not go below 0.6, whereas in FTCS we could have gone all the way up to 0, right. And what happens if you take a much larger value of Peclet number, that is of the order of 1, and then what you notice that finally you started seeing instability. So, now the range has gone from -3 to +1. So, what I have done here, I have drawn that -1 line here, we have drawn a -1 line here. So, to the left of which this region is your unstable region. So, if you take explicit methods for value of lambda below this critical value, what will happen? You have to worry about some values of kh which are going to be unstable, right. So, that is something you have to worry about. However, if you take value of lambda above this critical value, then you have a fully stable method for all the kh range, right, that you have resolved with your grid. So, this critical value happens to be about 0.2506. So, all that you are able to see now, that you can get a very spectacular improvement in your ability to take much larger time steps. See, these values of Peclet number are few orders of magnitude larger than what you can do with the explicit method. So, we are talking about improvement of the order of say 1000 times, 10,000 times, that type of improvement in computing. Okay, so this is what is all about the classical way of looking at parabolic equation and their computations. There is only one thing that I have not talked about, which I would like to tell you is this is more from a practicality point of view, not specifically related to parabolic equation, but in many computing problems what happens is we come across conditions where we state that the variables are periodic in nature. So, what does it mean? When I say the variables are periodic in nature, what we are talking about is that these values are repeated. So, whatever the value I have here, so if I call that as u 1 j, that will be equal to say u n j. So, the function is repeating itself. That is what you usually do with your Fourier series analysis, right. If a function is periodic, then you say look, this is my the wavelength. So, it is going to be periodic like this, and then we should be doing this. Now, all that I am going to ask you now to help me in writing down the discrete equation. See, the earlier what we had, earlier we had written B 1 x 1 plus C 1 x 2 equal to 0 was the first line. So, this was when we did not have any periodicity involved. So, I will call them as non-periodic problem. And the second line had A 1 x 1 plus B 2 x 2 plus C 2 x 3 equal to 0 and so on and so forth. That is why you had that A matrix that when we wrote, I wrote B 1 all the way up to B n, and then we had here C 1 all the way up to C n minus 1, there is 0 0, right. And what was your x vector? X vector from x 2 x 3 all the way up to x n minus 1, right. That is what we had. Now, if I look at periodic problem, what I am talking about now, my unknowns, basically I do not have a Dirichlet condition. Instead, the boundary condition is the periodic boundary condition, that is what I wrote. So, basically my unknowns will be what? If I were to write x vector, so I could start from x 2 all the way up to x n. Now, you see the difference, because why did not I write x 1? Because x 1 equal to x n. So, I am just simply noticing that here the number of unknowns were n minus 2, here it is n minus 1. Okay? So, dimension is bigger. What about the A matrix? What will be the A matrix? Well, I wrote something totally wrong, none of you protested, but let me write it as this. R1, R2 and so on and so forth. So, there is a right hand side, right. That is how we got that implicit. So, now if I look at this, what did I do? I had a R1 prime. What was R1 prime? If you remember what I said, R1 prime was whatever R1 that I had, I also had a quantity called A1. If I look at the point, so if I have this as I equal to 1 and I am now writing the equation for what? I am writing the equation from 2 onwards, right. That is how I have catalogued the unknowns. So, if I write the equation for 2, then I have what here. So, for I equal to 2, let us write one of the equation that you will appreciate. You are going to get u1 j plus 1, that is an unknown, that is multiplied by a1. Then I have b1 u2 j plus 1 and c1 u3 j plus 1 is equal to r1, right. Now, what you are noticing that this quantity is not a Dirichlet quantity, right. Like earlier we could put it on the other side. So, what should I do now here? I use the periodic condition that is given there. So, I will write it as A1, U1 is UN, so, what has happened now to the A matrix? You can see that corresponding to the last entry, I have a non-zero A1, right. So, A matrix, if I were to, well, let me write it like this, I will remove this, okay. So, since you have noted this down, I will expect that you remember what we are doing. Okay. So, now if I were to write down the A matrix, the diagonal entry still remains the same B1, then I have the super diagonal. What about the A1 quantity? A1 quantity is nothing but, it will come here. Do you see that? That there are stacks of zeros and then you have here. Then of course, once we are in the other line, there is no such problem, right. Same way, what will be my last equation? The last equation, if you allow me to erase this part. So, we are not talking about non-periodic part is easy and done. Now, if I try to write the last equation, well, what would be that? That would be A n, tell me, n minus 1 j plus 1, right, plus B n well R n. Now, this looks quite okay, except the fact that what is this? Our unknowns are from 2 to n. So, what is n plus 1 doing there? What is the meaning of n plus 1? It will be what? So, x n plus 1 would be some point here, some fictitious point here, isn't it? If I write it for this, this is involving all these 3 nodes. What about this point? This actually will be here, right, because it is periodic. So, that is what we are going to do, that I am just simply going to write the same thing, but here I will write C n x 2 j plus 1 is equal to R n. So, now if I look at the last equation, then what we have here is that B n remains here and A n remains here and C n goes where? C n comes here, because that corresponds to x 2, right. So, this is the structure. So, what we have here is a periodic tridiagonal matrix. So, in the next class I will just tomorrow I will tell you how we handle periodic tridiagonal matrix. This is not exactly the replica of what we have done for non-periodic cases, and this periodic problems are far too many for us to really understand and digest. Okay.